Yes, we can see it.
Okay. So as yesterday or last class we talked about time response in regards to first order system, and we saw that with first order system it can be fully characterized by time constant, and all those design specification for first order system are actually a function of time constant. And then we say if time constant is small, then the system respond very fast. And we saw also relation between time constant and the pole. So if the pole is close to the origin on the left hand side of the S-plane, then we say we have a sluggish response. But if a pole is far away from the origin, then we have a very small time constant, which in turn gives a response that is faster. So today we'll proceed with second order system. And before I forget, please class rep, both of you class reps, make sure that I have class attendance for yesterday's class and today's class. So you pick 2 attendance from the secretary, and those who have attended today and yesterday, please sign to those 2 attendance. And also remember, you need to pick other two attendance for class 20. Is it the class of 11th? Was it 11? That is October. It was, yeah, for 12th and 13th class. 12th of October and 13th of October. Also, I need these 2, 12th and 13th, and today's class 3rd and 2nd yesterday. Sawa, class reps.
Yes.
Please, yeah. Okay. So we'll proceed with time response for second order system. First, we'll model our second order system and get a transfer function, which is actually a standard form of a second order system. Why is it important that we study second order system? Because all other higher order systems, we can reduce them to a second order system. So if you have a third order, fourth order, which is not a scope or in this course, but higher order systems are actually reduced back to second order system, so that they can be analyzed. So it's very important that we study second order systems. So for a second order system, we consider a transfer function or a model on the right hand side, where we have our open loop. We have our open loop. So we have our open loop transfer function, G being that as in K, S, and then Fs tau plus 1. Here we see this is a unity feedback. So here our H is equals to 1. So if we want to find a relationship between output and the input, that is C over R, we can use this formula. Remember our formula. But here our H is equals to 1. So we substitute K S tau plus 1 like that, and then again K S tau plus 1. So this is what we have in this equation here. That one there, and 1 here represents the sensor feedback or the feedback gain, that is H, which is equals to 1. When you simplify, you'll get this equation where our characteristic equation is actually of order 2. Remember, we say denominator of a transfer function, when we equate it to 0, we call that as characteristic equation. Okay, there's no characteristic equation. So if we divide, once we have that, if we make coefficient of s squared 1 such that we divide numerator and denominator by tau, we'll end up with something like this here. And this corresponds to a standard, we call it a standard second order system equation, which is actually omega n squared plus divided by s squared plus 2 delta omega n s plus omega n squared, where omega n is what we call it natural frequency of the system. So omega n is the natural frequency of the system, and delta, this is the damping ratio, where delta omega n is what we call a damping factor. So we'll see that in first order system, response was like this, right? But in second order system, we'll see that response is mostly like that. So these are the dampings, right? And the damping ratio is given by that. So our second order system is actually fully characterized by two variables: one, damping ratio, and two, natural frequency. And to natural frequency. So this is what we call prototype second order system equation. We also call this as standard equation for second order system. As I said earlier, it is fully characterized by these two variables: omega n, which is natural frequency. My pen is, oh boy. Okay. Okay, omega n, which is natural frequency, and delta, which is damping ratio. All right. So denominator of this equation is a second degree. That's why we call this a second order system. And there are two variables that characterize second order system. These are natural frequency of oscillation, that is omega n, in radians per second, and damping ratio, which is a dimensionless quantity. So as I said, equation 2 is also called a standard equation for a second order system. This is just repetition. What I said. So these two describe characteristic of a second order system, just as the time constant we used yesterday, we saw that it describes first order system. Delta omega n, that factor is what we call damping factor, and it controls the damping of the system, those oscillations until they fade out or they die out. And damping ratio is what we call actual damping factor over damping factor at critical damping. So when we talk about, we'll see that when we talk about critical damping is when delta is equals to 1. So what this equation says is damping ratio is actual damping factor divided by damping factor at what? At critical. So At critical, we have delta is equals to 1. So we have something that's why we are saying damping ratio is given by that, and it is a dimensionless quantity. Guys, can you see my screen? Hello?
Yes, we can.
Okay.
Yes, we can see the screen.
So depending on the damping ratio, we can have four different categories of a second order system. When we have a damping ratio which is less than 1, that is, it is greater than 0 but less than 1, then we call that is underdamp system, and the response, it has some oscillation. So towards the after the transit response, we have some oscillation. Critical damped, this is when we have a damping ratio equals to 1. So in this system, when we have damping ratio equals to 1, we don't have oscillations. We don't have oscillation. And overdamped also, we don't have oscillation for overdamped. That is when we have damping ratio equals to greater than 1. And for delta equals to 0 is what we call it undamped system, and here we have some sustained oscillation. So the system is throughout oscillating. So you'll have something like that. Here you'll have something like this one, it will go, and this one is a bit less, as in it's more sluggish than the other one. So different system, we can have four different type of second order response, depending on the damping ratio. So for undamped system, when we have this, will revisit again, when we have damping ratio equals to 0, this is when we have uh, two, two of the poles at what? At the imaginary axis. So when you have these two poles at the imaginary axis, this is when you have some oscillation. So you can see one is our input, right? And this one here is our output. So you can see they don't match. So it is oscillatory. So we don't need a system which behaves like this, right? For critically damped system, and another thing you should note for these slides is that most of these diagrams which I got from a textbook, they use zeta. So zeta, some books they use zeta, uh, and some books they use delta. So zeta and delta, these are what we call damping ratio. So some books you'll see they use this zeta here, and others like what we are using is delta. So when you see zeta in this diagram, these are actually the delta which we are talking about. So for critical damping, uh, the roots is when we have them on the negative real axis. So when you have roots on the negative real axis, or the poles at the negative real axis, this is when you'll get a damping ratio equals to 1. And we'll see all these equations as in the time response for these scenarios. The most important one is this one, which we'll deal with it most of the time, because it actually follows after a long time. after a long time, it actually follows our input. So you can see it goes up and then start to oscillate, and then after some time, that actually it goes through what it actually follows our input. And this is when we have complex conjugate on the on the left hand side of our S plane, right? On the left hand side of our S plane. Keynote, one thing to note is that all these poles which we are talking about are on the left hand side of our S plane. Next week, we'll see that when we have something on the right hand side of the S plane, this is when we get we get an instability. So when poles are on the other side, on the left side, or the half side of this S plane on the left side, then we say our system is actually stable if we have poles on that side. You can see difference between critically damped and overdamped is that this is overdamped. It actually takes longer for it to reach what? To reach the final value, or to move towards uh, the input or our desired output, right? Than this. So here you can see it takes longer to reach than the critically damped. But for underdamped, you'll see it response is faster. It's faster, and then we have some oscillatory. After that, it goes and follows our input, which that is a key thing in underdamped system. So in our case, we will only discuss time response of a second order system under the input of unit step. So we'll talk about unit step time response of a second order system. Why do we use a unit step response? Although in some books you'll see they'll start with they'll start with the impulse response, and then unit step, and then ramp. So the most important signal to test are impulse and what? And unit step. For our case, we'll just move on and look at unit step response. So why is it important to use this? First, as we discussed yesterday, I told you that it is very easy to generate step signal and test in the lab. And then also a step signal is sufficiently drastic. So because it's 0 and then it goes up to 1. So this will give will give us a way to also see how other system or how other inputs will behave, because it changes from 0 instantly to 1, right? Also, yesterday we saw that once we have a step response, we can easily get impulse response by differentiating, and the other way around. So once you have that, then you can get ramp, and you can also get what? An impulse system response. Also, application of step input is equivalent to application of numerous sinusoidal. This you have done it in lab from the Fourier. So if you have so many disturbances, then this, or so many sinusoidal signal on a certain range, then we know that they tend to be in like a square or a step input. So let's move on this. So for unit step response of a second order system, we have our transfer function for a second order system given by this here. So for us to apply a unit step response, we need to apply a unit step. So unit step, this can be a voltage. It can be a voltage of 1. It can be a unit value. So we know that for our Laplace, then that will be 1 over s. So you apply that, and then you end up with that equation. So for us to get C of t, we need to get inverse Laplace of this, right? Remember yesterday we say for us to get time response, first we apply an input, we simplify, and then we get inverse of that simplification of Laplace, okay, of C of s. So here we have applied this input. We need to simplify this, and then take inverse Laplace of that simplification. And this will depend with different value of damping ratio. So we look at with different cases, like when delta is equals to 0, what is the response? And this will be similar to what we have seen here, but now we are trying to get the equations which will correspond to these curves. That is what we call time response, right? So for delta, that is underdamped case where we have delta is less than 1, we can rearrange our equation C of s in this form here. So when you simplify this, you'll see that it is actually in that form. So we can rearrange in that form. So when we do that, we can move ahead and also change this such that you can have s omega n plus this part here as that, and then you divide with that the denominator, right? Here you see we have something called omega d. Omega d is what we call damped natural frequency, and it is given by this when delta is less than 1. So once you have that, you can apply inverse Laplace from the tables, and this is what you will get, right? In the notes which I shared yesterday, you can follow with a different derivation, which is more logical, as in you'll get residues using partial fractions, and then from there you insert back those residues and then get inverse. So you can follow that in the notes which I gave. So the resultant equation is what we have here. It is good to know how to derive this, but don't expect that in an exam me asking you derive this. No. So mostly you'll be using these equations, but it's good for you to go through them to see how these are coming up. So this is the final equation for underdamped. That is the case where damping ratio is less than 1. So this is the response, right? And from here we can see that we have some oscillations And these oscillations, because of this sign, we have some oscillation, and this oscillation actually it's because of the damped natural.
Then at 0, we have a change from good negative. So we expect we are going to get
So this guy is like attending 2 lectures. I don't know, maybe is he repeating this thing? Huh? Garang. I think he's attending 2 lectures. Okay. So we can see that for this response, we have some oscillations. Yeah? And these oscillations depend on what? Depend on the damped natural frequency, which we just defined from the previous slide, which is omega d, right? So, and this is because of that that sign. So we have some decaying decaying exponent here, and these are actually oscillatory. So that's why you are seeing these as in, and then they die out as time goes to infinity. As time goes to infinity. So it is, if we have a frequency of oscillation as damped natural frequency, then obviously this varies with damping ratio, because omega t is given by that, so it varies with that damping ratio. Another thing to see is to get the error between our input and our output. So for this case, this is our output response. Our input was what? Was 1. Remember, this is a unit step. So we can get this error as a function of t by taking RT minus CT. So 1 minus this, it will be 0, and then that minus with that minus, it is positive. That's why we have this equation here. And as t goes to infinity, we can see this value here goes to 0. So as t goes to infinity, there is no error between the input and the output, and that is what we want. And also we want a system that will respond faster and follows the input, right? So you can see if we send t to infinity, then the whole of that it's actually tends to 0, and then E of t is equals to 0. So we can say at steady state, or when t tends to infinity, there is no error between input and output, or we can say the output follows the input. So this, we have discussed this. Now, if damping ratio is equals to 0, then we say the response become undamped, and oscillations continue. So we say we have sustained oscillations, and we don't want that thing in our system. So if we go to equation 3, this is where is equation 3? if we go to equation, if you go to this equation and this equation here, and you set delta to zero, that is damping ratio to 0, then you'll end up with 1 minus cos omega dt, that is here, omega nt, cos, because here the omega d is actually, and when delta is 0, we have just omega n. So when you set delta equals to 0, then you'll end up with this equation. You can see now, we just have what? We have sustained oscillations. So we have oscillation throughout, and our input is just 1, and then we have, so this is not a good system. And this happens when you have poles on the imaginary axis. So when you have poles on the imaginary axis, we say we have sustained oscillations, and the system is undamped. Someone wants to join. Okay. No, but Garang, I had someone giving a lecture there. Hmm? Okay, that is noted. So again, if we have delta equals to 1, then as we said earlier, that is what we call a critically damped case, and the poles are actually on the negative real axis, as we have seen here. The time response for second order system when delta equals to 1 is given by this equation here. Also, we can see as t goes to infinity, we don't have any oscillations, right? We don't have any oscillations. Okay. For a case where damping ratio is greater than 1, that is overdamped case, we have a response given by that which has 2 decaying exponent terms, and these give rise to a more sluggish system than the critically damped case, right? Than the critically damped case as it is shown here. And the roots are on the negative real axis. In a critically damped case, these 2 roots are equal. You see, these are equal roots. They are the same. They are 2, but they are the same. Here, these 2 roots, they are on the negative real axis, but they are not equal. You can see here you have minus, and this one is plus. So we have 2 exponents, and the system is actually sluggish. We call that system an overdamped case. So if we summarize unit step response with various damping ratio, that is from 0 to greater than 1, we can see between 4 and 8, that is where we need our system to be in with those damping ratio, depending on what we have seen in different cases. And for small value of damping ratio, that is 0.4, less than 0.4, we can see we have large overshoots. Like this one, it's too high, large overshoots. So we don't want that. We don't want these large overshoots. And for large values of delta, you can see they are more sluggish. So best way is to have system between 0.4 and 0.8. And mostly you'll see when we are doing this, we are saying that delta is equals to 0.7. So a system which is in between 0.4 and 0.8, that is a more desirable system than when we have less than 0.4 and more than 0.8. Because of this, it doesn't respond faster, and because of these maximum overshoots. Any question?
Yes, hello, sir.
Yes.
Yeah, for let's say a system where we require oscillations, will we use the case where the damping factor is 0, because you've showed us that it has sustained oscillations.
For oscillations, remember when we introduce feedback, we said for a positive feedback, that is where you will get oscillation. So a system with a positive feedback, that is where you'll get oscillations. So in electronics, when you want to get oscillation, they use that positive feedback, especially in oscillators. They use a positive feedback to get those oscillations. But in control, we don't use we don't set system for us to get sustained oscillation, because remember, we want our input to correct our output to follow our input. So if the input is 1, we want our output also to be along that 1. Is that clear?
Yes, it's very clear. Thanks.
So when we are designing this system, you might be given like a designer want like to set a system to a certain value, so that you know how fast will respond to an input or a desired output, and what is the error between the output, the desired output, and what we have, the desired output and the input, right? And we'll also want to see if that system will oscillate by how much around the desired value. So these time domain specifications are almost the same with what we discussed in first order system. Some of them, we'll see we have others. So in second order system, we'll talk about delay time, rise time, peak time, and also maximum overshoot. So maximum overshoot, this is our input. And also remember, this is the desired what? The desired output we want. But this system, you can see it moves up, and then we have this peak here. So the peak, the value from here to our desired output or our input is what we call maximum overshoot, right? And time, delay time, rise time, peak time, these are unsettling time. The definitions are the same as what we have discussed in first order system, right? So let's move ahead. And so time delay, the delay time is the time required for the response to reach half of the final value for the very first time. That is what we know from first order system. So same thing applies here, but the equations are different. We'll see. Rise time, same thing. So rise time, this is the time required for the response to rise to 100 of its final value. Peak time, peak time is the time required for the response to reach first peak. So this is the peak time from here to here. So this is the first peak. So this is first peak, and this is second peak. So first peak, second peak, and this is first undershoot, and that is second undershoot, right? So this is first peak like that, and then this is a second peak. So we defined TP for first peak. So the peak time is the time required for the response to reach first peak of the overshoot. So this is overshoot and this is undershoot. So that is first overshoot and this is first undershoot. That is second overshoot. So maximum overshoot is the maximum peak value of the response measured from the unit, and it is given by this. So this value here, and when CT tends to infinity, so that that is what we call percent overshoot. Settling time is the time required for the response curve to reach and stay within the range about final value. So we'll talk about tolerance of 2% and 5% as we saw in first order system. So this is what we are calling a settling time. So from here to here, and that tolerance between the final value. So if we go back and look at definition of rise time, we say it is the time required for the response to reach 100% of the steady state value for underdamped system. So here we are talking about underdamped system, and we know our response is given by this for the underdamped system. Where theta is tan inverse so from the definition, it means CT, for CT equals to 1, it means we have TR, our T is actually TR, right? So we can write it like this: CT equals to 1, sorry, Ct for t is equals to tr, we have 1 because it has reached 100%, and our input is, and desired output is 1 unit step. So Ct is equals to 1. So what we can do, we can plug 1 here, 1. So when you move this on the other side, you'll have and then sine equals to what? So this will be equals to and dt. That will be equals to and dt Imelda Juta. And dt and dt. Yeah. Gasheru. Hello? So this one will be equals to what from here? Guys, anyone? Hello? It will be equals to 0. It will be equals to 0, and this factor will disappear, because if we multiply this one here and on this side, it will be 0. If we divide also on this side, we'll just have 1. On that side, it will be also 0, right? So this will disappear because of that 0 here. And for us to compare, we can say sine 0 is also sine of 180, right? Or we can, it's same as sine of 180. Sine of 180 is 0, right? Sine of 360 is 0. So we can say this is actually n pi, where n is equals to 1, 2, 3, blah, 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 like that. So now we have sine omega d plus theta is equals to n pi. N pi, right? Is that okay, guys? Hello? Hello?
Yes.
Okay. So we'll have sine omega d plus theta is equals to sine pi. So omega dt plus theta is equals to pi. Our t, remember, is tr, right? So tr is pi minus theta over that. So that is our rise time. So where theta is tan inverse and omega d is the damped natural frequency. So this is the formula for rise time. So we have pi minus theta over omega d. Guys, are you okay there?
Yes.
Hello?
Yes.
Okay. So for peak time, from the definition, for us to get peak time, we need to differentiate to get derivative of Ct, and then we set it to 0 for us to get the maximums, to get that peak. And then we set our T equals to what? Our T equals to Tp. So for us to get Tp, what we need to do is equals to 0. So we need to differentiate this big equation this. And you can see we have T here and also T. So you'll apply product rule. So you apply product rule, you differentiate, you consider one, differentiate it, you differentiate the other, and then plus you consider the other and differentiate again like that, and then you set it to 0 with T is equals to Tp, then you'll be able to get what Tp is, right? So you'll end up, I don't want to do this, but you can get it from the notes. You'll end up with something like Tp equals to sine n pi. So Tp is equals to n pi. Tp is equals to n pi over omega. But for our case, for Tp, it is first what? It is first overshoot. So it means n is equals to 1. So Tp is pi over omega d. It is pi over omega d. So if you want to get this value here, that is Tp pi over omega d, this value here, Tp. If you want to get the time at the first undershoot, then it means you have something like 2 pi over omega d. And the time at second overshoot here, it means you have 3 pi over omega d as your T here. So is that clear? Hello? Guys, is that clear?
Yes.
Okay. We saw formula for maximum overshoot as and from the diagram, so if this is maximum overshoot and this is our desired input, which is 1, then we can actually get this value here from here to here, that is a maximum overshoot as so this value at that point is when we have Tp. So response at Tp minus 1, right? And it is -1 because of a unit step. So we can get our maximum overshoot as time response at Tp minus -1. And this is same as 1 minus, if we go to that equation, our famous time response equation, sine omega dt plus 5 minus 1. So this one is, and we have our t as Tp. We have our t as Tp, right? So we have our t let me just move to this. So we have here is equals to Ctp minus 1, and Ct is 1 minus E t squared sine omega dt plus 5 minus 1. So this bracket is what we have as that, and that one is, so when you bring 1 minus 1 is 0, so we'll end up with minus Tp sine plus 5, right? So what is Tp? What is Tp, guys? Hello?
It's peak time.
Yeah, value. It is pi over omega d, right? So maximum overshoot is minus into delta omega n, and then Tp here is pi omega d over minus that into omega d multiplied by pi over omega d plus 5. So that is here omega d we can cancel with omega n, so we'll end up with pi over 1 minus divided by sine, you have minus that one, and that one remain with pi 5. So this one is the same as minus 5. So pi plus 5 same as minus sine 5. So if that is the case, then this minus will go out, sine 5. So we'll remain with sine 5, right? So we know that phi is tan inverse over that, right? Which is, we can say tan phi is, this will imply that tan phi over cos phi is equals to, so sin phi is actually this this numerator here. So we say MP is 1 over times, so these two will cancel, we get our maximum overshoot. We get our maximum overshoot as that. So that is maximum overshoot, and percent maximum overshoot is just 100 multiplied by that factor. Sawa sawa. Hello? Hello? Guys? Emmanuel?
Yeah, we on.
Yeah, yes, Peter. Yeah. So it is good that you go and practice how to derive this, so that these equations are not strange to you, because, and also labda pass time, just doing math. But the thing is, I won't ask questions like derive this or find, no. Those they won't come in exams. But applying these formulas, uh, those questions, you will be tested. So it's good to practice so that you can be familiar with this, and you can in long run you can memorize these equations. So for settling time, this is similar. You can follow same approach, but here now you need to use the envelopes, but the formulas are the same. So T of S is actually 4, it's almost the same, that for 2% tolerance, and T of S is actually 3 over omega 4 for 5, I think for 4, you can check, for 5 I think, or for 4, you can check this, right? You can check. So I want to derive that, and also time constant, it is given by 1 over time constant is given by 1 over actually reciprocal of the damping factor. So reciprocal of the damping factor is what we call it, is what we get as time constant. So just to move to questions, you are told to obtain the impulse and step response of the following unity feedback control system with open loop transfer function as, so G of S is equals to, so you are told to get step response and the impulse response for this system. So this is an open loop transfer function in a unity feedback. So it means we have something like this. plus. So in control, if the nature of feedback is not stated, then you assume it's a negative feedback, right? Unless you are told this is a positive feedback. So if you are just the question just states unity feedback, then you know that is a negative feedback, unless you are it's stated that it is a positive feedback. So that is our model. So we need to get a step response. Therefore, we need to get C of t, and that C of t is, so we need that. So C over R is equals to G1 plus GH, but we know our H is 1. So that is the equation. So C S is actually RS multiplied by G1 plus G. So for unit step, we have S, and here we can have 6. So C of S is, if you simplify that, you'll get something like this. We have 6 plus 5S plus 6. So that is our C of S. So you need to get C. For you to get C of t, you use partial fractions. You'll have a1 over s plus a2 over s plus 2, a3 over s plus 3. So if you factor that, have s plus 2 and s plus 3. That's why we have. So for partial fractions, your a1 will be what? A1, what is A1? A1 is 1, and A2, what is A2? Kimiti, Brian, what is A2? Brian. A2? Brian, what is A2? You're telling me yes. What is A2? Here. What is A2 here? Guys, okay, you are in the lab, you can't speak. Just write. Just send a message. What is A2? Ali Mohammed. Ali Mohammed. Ali Mohammed. Class rep?
Yes, sir.
So what is A2 class rep? Okay, -3. I hope you guys are not just. So taking inverse of that, we have 1 -3 2t plus 2at, like that. So that is a response, unit step response. For you to get impulse response, you just what? You just differentiate this. So you'll have 6 minus 6, which is 6. Okay. So let's do another question, another example. You are given this figure. And then the question is, reduce the block diagram to derive the transfer function of the system. Find the value of K that will result in a critically damped case. So what is K? Delta is equals to 1, critically damped case. So we know we can get our ys over our x, like that. So we know this from the denominator. This is a second order system, so we can compare this with our standard second order system. Therefore, from there we can say K is omega, that's K, and that's K is omega squared. And this value here is the same as that one. So that is equals to 20. For critically case, we have the delta equals to 1. So here we have 2 omega n is equals to 20, because we are told for a critically damped case. So and from there we have omega n is equals to 10. So our k is 10 squared, which is 100. So there are several questions. In fact, in this area, there are several questions you can practice. I'll try to send you guys these questions for you to practice. But next week we'll do one or two more questions, if that's okay with you. So we'll do one, I think one or two. Yeah. One or two questions, and then we start error analysis. So this is what I intended to present today. Is there any question? Class rep? Any question? Hello?
Yes, excuse me, sir.
Yes.
Yeah, for the rising time, I think my network was a bit off, but I noticed we found the value and the signal got to 100%, but initially we did from 10% to 90%. Maybe you could clarify. Thanks.
Okay. For first order systems, if we go through the notes, for first order systems, this is where we consider between 10 and 10% and 9% as rise time. Also, for the case where we have overdamped, we have an overdamped case. But for underdamped case, the rise time is defined as the time required for the response to reach 100% of the steady state value for the underdamped case. So for the underdamped case, the definition is 100%, the time to reach 100%. And when we have overdamped case, that is when we use that definition of first order system. That's why in our derivation, since the equation, time response equation we got, it's underdamped case, because we considered all these specifications which we developed and derived. These are based on the underdamped case when we have delta less than 1. Remember, we say we have when we want a desirable system, we need to have a damping ratio between 0.4 and 8. That's why we are using delta less than 1, and that's why we are concentrating on underdamped case. That's okay, Samuel?
Yes, thank you for that, sir.
So please, class rep, make sure I get 4 attendants on 12th and 13th, and 2nd and 3rd. So 4 attendants, 12 and 13.